Okay, some other good terminology you need to know. First, economies of scale. Scale means what happens to your business when everything scales up, everything gets bigger. So instead of being a firm with one factory and one manager and 100 employees, we're asking what would happen if I had 2 factories and 2 managers and 200 employees. Economies is asking what's my per unit cost of production. Now there are some other ways we'll think about defining this, but it really gets to asking what happens to my cost per unit. If you scale up your business, if you make it larger in all ways, if you do that and your cost per unit goes down, we say you have economies of scale. You make your firm larger, your cost per unit goes down, economies of scale. If you make your firm larger, and I mean scaling everything up, land, labor, capital, and entrepreneurship, scale everything up. If you scale everything up and your cost per unit goes up, we call that diseconomies of scale. Diseconomies of scale. Sometimes we'll also call this decreasing returns to scale. If you scale up your business and your cost per unit stays the same, we'll call that constant returns to scale. Economies of scope, on the other hand. Scope means how broad are the range of products that you make. So if you increase the scope of your business, suppose you're a computer manufacturer, you might increase the scope of your business from just making laptops to making laptops and desktops and servers and software. You're increasing the scope of your business. If you decrease the scope, you might just drop all that other stuff and focus on doing one thing. Economies of scope means it's more efficient. If you find you have economies of scope, it might be more efficient to do more things, to increase your scope. So you might find that you can produce more efficiently if instead of just making laptops, you decide to make laptops and desktop computers. You might find the opposite though, and we'd call that diseconomies of scope. So again, economies of scope, it might be more efficient, lower your cost per unit if you expand the number of things that you produce. Now let's review a couple of things we did last time very briefly. Remember the equation 1 that we were talking about. The marginal rate of technical substitution is the slope of an what? An isoquant. So an isoquant is what we're calling an indifference curve now. So marginal rate of technical substitution is the slope of an isoquant. To find marginal rate of technical substitution, you can find the marginal product of labor divided by the marginal product of capital. This is assuming that when we make our graphs, that we are putting labor on the x-axis and capital on the y-axis. And when we have these isoquants, the slope of the isoquant at a point is the marginal rate of technical substitution. What it tells us is how many machines we could give up if we increased by having one more worker. So how many machines could we shut down if we got one more worker? It's rise over run. Rise is machines we shut down, run getting one more worker. You could think about it the opposite way. Suppose one worker does not show up for work, we lose a worker. How many more machines do we need to obtain to replace the worker? Marginal rate of technical substitution. It's just the slope of an isoquant. And in that first equation, we're setting that slope equal to the slope of the budget line. But now we don't call them budget lines, we call them isocosts, right? And so when we're looking for the solutions to these problems, we're trying to minimize the cost of producing a certain number of units of goods. What we want to do is find, let me just draw an isocost here. What we want to do is take that isocost and move it as close to the origin as possible. That means we're lowering our costs, right? Remember with a budget line, when we give somebody more money, that shifts their budget line out. As a business, you want to shift this budget line in, lower costs, lower costs, lower costs, lower costs, until you find the budget line that is just barely tangent to your ISO quant at one point. So find the lowest ISO cost tangent to your ISO quant, and where those two touch at just one point, that's going to tell you the optimal amount of labor and capital to produce that certain number of units. How many units? Well, suppose this is the ISO quant for 100 units. So we want to find what is the cheapest combination of labor and capital to minimize our cost to produce 100 units. And then we want to calculate the total cost of doing that. Now, one thing we'll find as a side effect of doing this kind of optimization, trying to minimize the cost, is when we find this result, we're going to find as a side effect, and I'll show you why in just a second, that there's going to be this result that in economics we call the equal marginal output per last dollar spent on a unit of an input rule. Whew, what does that mean? Okay, let's do just a tiny bit of very simple algebra here. If we take this equation, the marginal product of labor tells us how much additional output we get for adding one more worker. Marginal product of capital, how much additional output we get for adding one more machine. We set that equal to the amount we pay our workers per unit and the amount we pay for our machines per unit. So W for wage, R for the rental rate of capital. If we rewrite this equation, let's multiply both sides by marginal product of capital and then divide both sides by W. And what we get is something like this. Marginal product of labor divided by W. All right, so we're just moving that over there by dividing both sides by W. And multiply both sides by the marginal product of capital. That's going to move that up there where W was. Marginal product of capital divided by the cost per unit of capital. To make this a little easier to understand, let's put some numbers here. Suppose that where we are right now, the last worker we hired gave us 10 more units of output, and we had to pay that worker $5 for that last hour that they worked. So what does that mean if we paid our worker $5 for the last hour they worked and we got 10 units of output? Well, how much output per dollar are we getting from that worker? Well, 10 divided by 5 tells us we're getting 2 units of output per dollar we paid that worker. This rule just says that has to be true for our machinery, for our capital as well, if we are doing things in the optimal way. Because all we've done is rearrange this equation that says we're minimizing costs, because the slope of the ISO quant is equal to the slope of the ISO cost. So if machines cost us $10 per unit, if we are really optimizing, if we're really minimizing costs, then we had better be getting how many units of output out of the last machine that we got? Well, this ratio has also got to give us 2 units per dollar. So we'd better be getting 20 units of output, since 20 divided by 10 would also mean that we're getting 2 units of output per dollar spent. What if we found this wasn't true? What if they were not equal, because we found that when we did this, we actually got 40 units of output from the last machine, and the machine cost us $10. And we got 10 units of output for the person, and the person cost us $5, then they're not equal. That means we're not doing things right. Can you tell me what we could do? In what direction should we move to try to get more bang for our buck? Well, over here for machines, this is telling us that that last machine gave us more bang for our buck. Bang for our buck meaning we got 4 units of output for the last machine per dollar we spent on it. So if you're a manager and you sit there and you have money in your hands and you can imagine yourself just allocating dollars to different resources, always allocate your dollars toward the thing that has given you more additional units of output per dollar you have to spend on it instead of the thing that gives you less units of additional output per dollar you spend on it, right? So this observation is what we call the equal marginal output per last dollar spent rule. There are other ways people describe this and different terminology people use, but it's all coming down to the same thing there. Last thing I want to go over in this video, and also getting back to what we did last time to try to refresh our memory a little bit, the expansion path. The definition of an expansion path. What we want to know is, if we're a company and we expand our output, that's what we mean by expansion path. As we expand our output, what does the optimal combination of capital and labor look like? So if we were to draw a graph where we're expanding output and we want to know the optimal combinations of labor and capital, what would that actually look like? Let's go back up to our graph that we looked at in the last video. Let me erase this green one here. So what we found last time was that if we wanted to produce 150 units of output right here, then the cheapest way to do it when the wages cost $5 per worker and capital cost $10 per unit, the cheapest way was to get 19.4 workers and 7.76 machines. And we graphed that point here as the orange point. So that's with 150 units. If we wanted to draw an expansion path, what we would want to do is say, okay, what if we went up to a higher level of output, say this green isoquant here, which would be 200 units of output, and then 250, 300, 350, 400, and we looked at a lot of different levels of output we could choose. What do all these solutions look like for the optimal amount of capital and labor to use at different production levels? What we could do here, let's just do one quick problem here to refresh ourselves. Remember our two equations we have. The marginal rate of technical substitution, well, our production function is 15 L to the 0.5 times K to the 0.4. So our marginal rate of technical substitution using our shortcut trick was 0.5 K over 0.4 L equals 5 over 10, because this is the wage 5 over the rental rate of capital 10. And then our second equation was 150 equals 15 L to the 0.5 times K to the 0.4. If we wanted to solve this problem again using a different output level, then everything over here for equation 1 is going to be exactly the same. So instead of starting from scratch, we just take this, the prices aren't changing, and the production function isn't changing, and we would say, okay, we simplified that down to K equals 0.4 L. So equation 1 is just going to be K equals 0.4 L. And then equation 2, if we wanted to solve this for lots of different output levels, is just going to be, okay, fill in your output level, equals 15 times L to the 0.5 times K to the 0.4. And we would just solve this problem again and again and again and again. And what we would end up doing is just always plugging this 0.4 L into this second equation for K and solving for those optimal amounts. But when you have a Cobb-Douglas production function like this, it's actually a lot simpler if all you want to do is figure out what the expansion path looks like. And here's how we can do it. Let's just look at this equation, K equals 0.4 L, and let's graph it. K equals 0.4 L. So K is on the y-axis, so this is kind of like y equals 0.4x, right? And what's the y-intercept of that equation? 0, right? So, okay, here's 1 point. Let me do it in a different color than red. Okay, blue. So there's our y-intercept down there. And what's the slope? Oh, the slope is 0.4, so that means we go over 1 up 0.4, over 1 up 0.4. Or we could go over 10 and up 4, right? Or we could plug some values in here and see what we get. Let's see, over 20 and then up 0.4 times 20, right? That'd be 8. So what's this line going to look like if we graphed it? We're going to start here at the y-intercept, and we're going to go over 10 and up 4. We're going to go over 20 and up 8. And we're going to go over 30, and 30 times 0.4 is 12. Hey, wait a minute. We know that whatever line we draw has to go through that orange point that we solved before, right? Because all we're trying to do is come up with a graphical view of all these optimum points. And all these optimal points have to satisfy this equation, k equals 0.4L. And so this is our expansion path right here. And that just tells us that as long as the prices of labor and capital remain the same, and they are $5 and $10, then the cheapest way to produce any number of units is going to be somewhere along this expansion path, somewhere along this blue line, where the equation is k equals 0.4L. Kind of simple, right? But this is one of those things that after someone shows it to you, it does look pretty simple. But if somebody just walked up to you and asked you the question, hey, what's the equation for the expansion path? It'd take you quite a bit of thinking to get that. So that brings us to the last item on our list here of things I wanted to go ahead and talk about, and that's the idea of a long-run total cost function. I guess first we have to talk about what's the difference between the long run and the short run in an economics class. Well, at least in a microeconomics class. The short run is a short enough time to where at least one input is fixed. If we're looking at these models where we just have labor and capital, normally we'll assume that capital is the thing that is probably going to be harder to change or take longer time to change. Labor, most of the time, you just say, hey guys, can you stay later? Or, oop, I got to send you home today early. You can increase or decrease the number of hours your employees work. You can bring in temporary workers. Usually doesn't take you a lot of time. It's something you can probably do on an hourly or daily basis. But with capital, machines, buildings, equipment, things like that, depends on the kind of business. But it might take you a couple of days, a couple of weeks, or a couple of years to expand your capital depending on what kind of business you're in. If you're an airport, it might take you 5 or 10 years to get the permits and get the designs and build some new runways, for example. But for some businesses, it'll be easier than others. So a long-run total cost function, what we're trying to get at, we're not going to actually do the math to derive one today, but what we're trying to get at is get some kind of function where total cost is some kind of function of quantity, but then where the quantity we're producing is itself some kind of function of capital and labor. This mathematical jargon that I just wrote down here is just a way of saying that in the long run, capital and labor are both variable, and they, as we vary capital and labor, they cause quantity of output to change, and as those things change, that affects our total cost. In the short run, if we're going to assume that in most cases it would be capital that would be fixed in the short run, then we would say in the short run, our total cost is going to be a function of how much we want to produce, but the only thing we can really change, the only variable, is labor. That's why we'd call it a variable cost. So in the short run, variable costs are anything we can control right now. We can use more of, less of today to produce more or less output. Fixed costs are things that are not variable. In the short run, that would be capital, probably entrepreneurship as well, probably in some cases land. It just depends. Sometimes we say land also means raw materials. But in the short run, labor and materials would be variable, and capital would probably be fixed. So in the short run, we would just say, okay, well, as we produce more today in the short run, if we really literally want to take the shortest run case we can think of, then today I'm going to use more labor and materials as I produce more, not use more capital, because that is fixed. So in the next video, we're going to get back to doing some more mathematical analysis. But if you don't understand the terminology and where you're going and what it all means, doing the math just makes it into a math class. But that's what we'll get back into a little more of next time. So as always, if you have questions, please let me know. Otherwise, I wish you the best of luck in all your studies, guys. Bye-bye.